Hello and welcome back. So, we first finish one remaining problem in variation principle, then we will move to a new topic. Okay, so, the last problem which was due was surface of revolution is formed by making one curve passing between two fixed points x1 y1 and x2 y2 and revolving around y axis. Find out the curve for which surface area is minimal. So, this is a picture given here. So, basically you can consider it as if it is a thread and I am holding it at these 2 points and making it evolve around this vertical axis. So, here I have given this particular axis as y axis, it could be z axis also. I have given y because we typically use, so far we have used x and y as the variable. Okay. So, in order to solve this, let us assume that we have 2 points like this, and if I just hold this assuming that there is gravitation present, it will look something like this, and we know that this shape is called catenary, not exactly like this, but something like this. Okay. So, anyway, but right now we are, and if I now evolve it, let us say this is my axis, and if I have to evolve it around this particular axis, it will give you a surface which will look something like this. But right now this is not for the, we have to minimize the surface area. So, we have to take a curve which is not this, but some shape which is, let us say, like this, as also given hinted in the figure. Right. Now, in order to solve this, okay, we have taken this as x, this as y. So, what we do is we draw a circle, or basically we take a strip of area. Okay. So, the instantaneous radius is at this point. Okay. So, what we do is we take a slice on the xy plane. Essentially, it is a 3D problem. There is an axis here, we can call it the z axis. Okay. So, if we take any arbitrary radius at any arbitrary orientation, the radius will be given by r equal to x square plus z square. So, what we need to do is we need to find out the surface of this strip, and the surface of this strip is given by dA, which is equal to 2 pi r dl, dl being this length, the thickness. Okay. So, we take a strip which has a thickness dl and a radius r. Okay. But now, what happens is, as we are, so it is uniform, right. So, this surface of evolution is uniform. So, it does not matter if I stay on this point or we go to that point. So, I have chosen a point which is exactly in the y x plane. If you do that, then you immediately see your r square will be simply x square. R, sorry, there will be a root here. It was root x square plus z square, which will reduce to simply root of x square, which is nothing but x. Similarly, your dl in any arbitrary generalized position, let us say at this position, is root over of x square, or rather not x, but dx square plus dy square plus dz square. But once we take the slice in the xy plane, this dl also reduces and there is no z term. So, essentially what we did here, just by choosing this as y axis, choosing this as y axis and taking a slice or taking this length and radius along in the xy plane, we have reduced this 3D problem essentially into a 2D problem with two variables x and y, right. So, now it is easy. So, this we will write x root over, okay. Now, I have shown you many times how to write this, then we have to write dx 1 plus y dash square, where y dash is equal to dy dx. That is it. And so, total surface of evolution A will be integration of dA, which will be integration 2 pi x dx root over 1 plus y dash square. And this will give us f of x y y dashed as x root over 1 plus y dash square. There will be a factor of 2 pi, but because it is a constant factor and we have to take the equation from here, it will cancel out anyway. And please note that this function is right now the construction which we are using. This has x, it has y prime, but it does not have y. So, if I to take sorry, not L, del f del y prime minus del f del y equal to 0, we see that del f del y is equal to 0 anyway. Now, if this is the case, then this equal to 0, which implies this is a constant c, and this particular derivative is x root over, okay, so it will be 2 y prime y plus y prime square. Okay. And now we simplify this a bit, and from here we get the differential equation that y prime, which is dy dx, is, okay, so I will just give you the final form, is a by some constant a by root over x square minus s square, right. Okay. So, this is where we stand right now, and the solution of this will have the following form. The solution of this, okay. So, I told you in the previous problem in the last lecture, I could not write the final form of catenary equation. This happened to be the final form of catenary equation. I mean, not exactly, basically yeah, it will be there was a factor 1 over some factor was missing, but the solution of this will actually be y equal to a cos hyperbolic inverse, okay, x by a plus some constant b, where a and b, a is this constant and b is some arbitrary constant of integration. Okay. So, this is right. So, we see that this is y equal to a cos hyperbolic function, which will lead to a functional form of x, which is y minus b will come, yeah. So, it will be, yeah, a cos hyperbolic no inverse y minus b by a. So, you see, I mean, although it is not exactly a equation corresponding to cos hyperbolic function, it is strongly related, it is inverse of hyperbolic function, which can be expressed. So, basically x and y has a relation which is given by a hyperbola. So, that is all, that means also this curve, which will the shape of this curve which will produce minimum surface area, is also a form, I mean this is also a catenary, right. Okay. So, for a catenary, not only the freely hanging shape under gravitation will be a catenary, but also a surface of evolution which is produced by rotating a catenary will have minimum surface area. The same problem can be solved in a horizontal geometry as well. We can just take the chain like this and try to rotate it, and it can be shown that even this surface area will be a minimal. Okay. So, this is something which I am leaving it up to you for an exercise. The same problem essentially, instead of keeping it vertical, we are making the axis of evolution horizontal, right, axis of revolution horizontal. Great. So, I think that is it for variation integrals, and right now, okay. So, we have basically finished the chapter on Lagrangian as well. The last topic of Lagrangian was the variation integral. of course, any problem which we will we have come across so far during our discussion of Newtonian mechanics, except the problem of variable mass, can be tackled in terms of Lagrange's equation of motion. So, essentially Lagrange's equation, I mean Lagrange's formulation offers you just a new approach, a new pathway to the same set of equations. The equations we are getting are exactly identical. Of course, we have this kind of variation integral which is somehow related to Lagrange's Lagrange's formulation, but it's not necessary that we apply it only for classical mechanics. These are essentially static problems, right? The problem when a chain is hanging, and so it is hanging by minimizing its potential energy, which is a static problem. So, even that can be solved using variation integrals. Now, what I am trying to tell you that right now so far we have done, starting from the beginning of the course, we have learned, initially we reviewed the kinematics of associated with Newtonian mechanics, basic Newtonian mechanics. Then we went into central orbits. Of course, there were systems with variable masses and all. Then we moved into central orbit, rigid body dynamics. In between we had little bit exposure of moving coordinate system, which was once again used for rigid dynamics, and now we have learned how to handle the same set of problems with Lagrangian, except for the particular family of problem in which mass is changing as a function of time. That even that can be tackled using Lagrangian, but that is lot more difficult. Okay. So, so far whatever we have learned is different fundamental aspects of classical mechanics. Right now, the last topic of this lecture is probably the first area in which we will be applying all the techniques we have learned. Okay. So, this is the area which is relatively new. So far the areas we have studied, they were all developed during 16th and 17th and 18th century, but small oscillation is something which is much new in a sense that the latest developments of theory of small oscillation using quantum calculation is still going on, and people are still using it, I mean actively using it for analyzing spectroscopic results, vibrational levels of different molecules, and configuration of solids and all. So, this is a very active field still now, people are using it actively, and the mechanism what we will be following is a mixture of classical and the Newtonian and Lagrangian. I mean what I mean is what I should say is we will be using Lagrangian primarily to begin with, but slowly and slowly we will be going more into the details of matrix diagonalization and see what insight we can get about the system. And most importantly, we will be defining few quantities. One is normal coordinate, second is normal frequencies, and third is normal mode. Okay. So, typically we do this when we will be when we study oscillation. Normal modes and normal frequencies, they are typically defined for coupled oscillator systems. Could it be two coupled oscillators? Could it be more than two coupled oscillators? But generally for single oscillator, only one frequency is possible, and that is the normal frequency. So, we do not state that explicitly. When it comes to coupled system, we start defining these terms. But let me tell you something, strictly speaking, normal modes and normal coordinates, they are no way related to vibration only. Okay. So, let me start this discussion of small oscillation with a discussion on normal modes. Okay. So, typically people do it at, I mean typically we take the subject of normal mode towards the middle of the process, like when we come to that junction where we have to either forget about solving the equations, or we have to take normal mode solution and we can proceed. But for me, I think I have realized that it is better for the students if we start with a basic understanding of normal modes and normal coordinates. Okay. So, we start our discussion on normal modes, and let us say we take a diatomic molecule as a model system. What is a diatomic molecule? We have, let us say, two atoms or two atoms joined by a bond. So, right now we can forget about all the quantum mechanics associated with it. Of course, if it is a true diatomic molecule, I mean if the system is that small, there will be lots of quantum effects, uncertainty effects and what not. But right now let us forget about all this. Let us treat this system classically. Now, in a system where we have two masses, in a system where we have two masses and one, let us say, massless rod attaching these two, how many degrees of freedom do we expect? We typically expect, if it is a rigid system, then we expect 5 degrees of freedom. Why? Because total degree of freedom will be 3 into 3 plus 3, which is 6, but because there is a constraint condition, if it is a rigid rod which is holding this 2 in place, we take 1 degree of freedom out of the system and we have 5. Okay. But let us assume that it is not a rigid system. If it is a rigid system, there will be no vibration. Okay. So, if it is not a rigid system, that means if it is vibrating, how many degrees of freedom it can be? Now, it is essentially it is a 1D system. So, if we put the axis here x and z and let us say y is out of this plane. Okay. So, this is my x, z and okay, let us draw this y also. So, this is y. Okay, so, this is my axis system, or rather let us make it x, y, z, it will be easier. So, let us say no, actually bit difficult. Let us make this x. So, y is pointing in and z is up, right. This is the right handed system we follow. Okay. So, we have 5 degrees of freedom, but now we have vibration, and just by inspecting the system, I can tell you that vibration can occur only along the x axis. Y and z axis it cannot vibrate, it is a 2 molecule system. So, if it goes up and down like this around z axis, this will not be a vibration, but it will be a rotation, right. So, it can translate along x, it can translate along y, it can translate along z, it can rotate around y, it can rotate around z, and it can vibrate along x. So, these are all possible types of motion. So, we have translation, we have rotation, and we have vibration, right. How many types of translation are possible? As I said, it can translate along any of the axes. So, we have 1 plus 1 plus 1 equal to 3 types of translation. One is due to x, one is due to z, and the third one is due to y. Rotation, it cannot rotate around x because it is a, I mean, although it is, I have drawn it like this, it is essentially a one dimensional system. I mean, it is so tiny that rotation around its own axis will not be counted. So, there could be 2 rotations, one along y and one along z. So, here also I can draw it like this. How many vibrations? Only one, because as I said x and y it can rotate, it cannot vibrate. So, there is only one vibration which is along x. Now, let us say the coordinate is x 1 y 1 z 1 and for this it is x 2 y 2 z 2, the coordinate of the point masses, right. So, we have altogether 6 coordinates and we have altogether 6 degrees of freedom, 5 due to translation and rotation and 1 due to vibration, for altogether 6, and we have 6 coordinates. So, 3 plus 3 6, and in principle the 6 coordinates, I mean 6 number of coordinates should be sufficient in order to describe the system, describe all these types of motion, right. Now, what we will try to do is we try to find out a combination of these coordinates, each of which will talk about one particular type of motion. It could be a rotation around z, it could be a translation around x, along x, or it could be a vibration along along x, right. So, let us try to get the combinations which will give us the correct description. Let us first take the translation along x. So, if it translates either along this direction or along that direction, both the masses will follow the same direction. For a translation, it will just move like this or like this, the whole system. So, if a translation is taking place along, let us say, positive x direction, that means x 2 is increasing and x 1 is decreasing. So, if I take a combination which is x 2 minus x 1, this will always be increasing, right, because x 1 and x 2 they have opposite sign. Similarly, for combination which is x 1 minus x 2 will give a translation along negative y axis, negative x axis. So, what I can do is, and now forget about this positive negative business, what I can do is we can put a plus minus sign here to take care of that, and I can tell you that plus minus x 2 minus x 1 is responsible for it will be taking care of any translation which will be happening along x axis. Now, for y axis, when a translation is happening along y axis, both y 1 and y 2 will increase. Similarly, for a translation which is happening along positive z axis, both z 1 and z 2 will increase. If it is happening at negative z axis, both z 1 and z 2 will decrease. So, if I take a combination which is plus minus y 1 plus y 2 and plus minus z 1 plus z 2, y 1 plus y 2 and z 1 plus z 2, both of this will give you translation along y and z respectively, is not it? Think of it. X is something different, because in x there are 2 coordinates. So, origin is here, one has a positive coordinate, one has a negative coordinate with respect to the origin, but for y and z both changes in the same direction. When it moves along z, both gains in z 1 and z 2. If it goes along minus y, let us say along this direction, both loses in terms of y 1 and y 2. So, these are the right coordinates. These combinations of coordinate will give you translations around x, along x, y and z. Now, for rotation around z, what happens? If it rotates around z, let us say in this direction, this molecule, the y component of this molecule, or let us say about y axis. So, y axis is kind of pointing into the board. Now, if it rotates around along y axis, so this one goes up and this one comes down. So, if this one goes up, it will gain in z 2, and if it comes down at the same time, it will lose in z 1. Okay. So, if I take a combination of plus minus z 1 plus or z 1 minus z 2, this is good enough to give me a rotation around y axis. Think of it. When it rotates around y axis, this combination will always increase. So, either Z1 is going up and Z2 is coming down. So, Z1 minus Z2 will always be positive or the other way around. Whatever it is, this will give you a rotation around Y1, Y. Similarly, a combination of Y1 minus Y2 will give you a rotation around Z. Okay. So, we have 1, 2, 3, 4 and 5 coordinates already, which will 5 coordinates which are combination of this original x, y, z coordinates, which will purely give you one of the motions, I mean which will be responsible for one of these possible motions. Similarly, for the last one, which is the vibration, see what happens in a vibration. In vibration, if x1, I mean this one goes in this direction, this mass, this one goes in the other direction like this, and when they come out at the same time. So, when x2 gaining, x1 is also gaining. When x2 losing the value, x1 is also losing the value. So, we need to, if we take the combination x1 plus x2, yeah, of course, there will be a plus and minus. Will it give, what will it give you? It will give you the vibration. When x1 increases, x2 also increases, both increases at the same time. Please remember that these are, so this is the right combination, very good. So, you see this, if I just now level them N1, N2, N3, N4 and N5 and N6, these are the combinations which will describe one of these types of motion independent of the other. So, when I am describing a motion which is a combination of, let us say, translation, rotation and vibration, I can take a suitable combination of these 6 coordinates. See, if I am having a slight doubt, maybe I have messed up with N1 and N6. I think these are right, but it might turn out that plus sign will give you translation and minus sign will give you vibration, which I have to think, and if it is wrong, then I will get back to you. But that is not the point here. Point is, I can find out a combination of coordinate which will purely talk about one particular type of motion, okay? And that is what we have done here, and if for any general motion which is a combination of rotation, a translation and what you call vibration, any combination of motion can be represented by a coordinate r, which is a linear combination of these ends. Okay. So, any general displacement of this system can be written in a linear combination of this N1 to N6 coordinates, N1, N2, N3, N4, N5 and N6, and these are your normal coordinates. So, if you have thought that normal coordinate is something that is only associated with vibration, you are totally wrong. Please keep that away from your head forever. Normal coordinate is something, any coordinate which is actually a combination of Cartesian coordinate which describes one particular type of motion, which describes only one type of motion. So, if I am talking about a translation, I have to choose between these 3. If I am talking about a rotation, I have to choose between here and vibration above here. So, all these are normal coordinates, and a general motion is a linear combination of this. Important is, all these are independent of each other. So, if a translation is happening, at the same time a rotation may also happen, right. Similarly, a vibration may also take place. So, all these coordinates, they are not only pointing, I mean describing one particular type of motion, they are all independent of each other. So, this is a set of coordinate which is also capable of serving as a generalized coordinate, because they are 6 in number and they are independent of each other. So, these are called the normal coordinates. Okay. So, now this is the fundamentals of normal coordinate, and as I said, I will check once again between n1 and n6. If I find if this is not right, then I will get back to you. Okay. Now, what we will do is we will just give you a very brief description of equilibrium before we stop this lecture, and we will continue from there in the next lecture. Now, so this is normal coordinate, which is has nothing to do with vibration as such, as in it's not no way it is related only to vibration, but what we are going to discuss is small oscillation, and in small oscillation it is all about vibration, right. So, what happens is before we go into the details of small oscillation, let me tell you how many types of equilibrium can exist in a system. In a system, we can have a stable equilibrium, we can have a metastable equilibrium, and we can have a unstable equilibrium. What are these? Let us take a 1D potential function, and I will demonstrate. I will just give you an idea of what is stable, what is metastable, and what is unstable. So, 1D means there is only one parameter. Okay. So, let us say we have our parameter q and v of q. If v of q have this shape, okay. So, we have there is a maxima here. Now, if a system of interest stays at the maxima, and if we perturb it slightly from a maximum position, what happens? If it comes, see, the force is always so force is the slope of a potential function at any point, because f is as we know is given by minus grad. So, in this case there is only one function, it will be dv dq, negative slope. So, here you see the slope is in this direction, right. So, the force will be driving it. If we deviate it slightly, the force which will be generated driving it away from the equilibrium, right. So, that means the system will fall, it will never go back to the equilibrium, it is not restoring in nature, but it will be driving away from it from this point. So, the system will fall out of equilibrium, and this is an example of unstable equilibrium. So, this is what is meant by unstable equilibrium. Okay. And then we have another situation in which we can have a potential, let us say like this. Okay. Actually, this is not a very good drawing, it should be even shallower. Yeah, we can have a function like this. So, we have a system here, we start deviating it from the equilibrium. So, there is a slight slope, let us say, or I can actually draw it in a slightly different manner. What I can do is I can make it look, yeah. So, let us say the system is here, okay. Start deviating it from this direction, restoring force will bring it back. Deviate it little more up to here, again the restoring force will bring it back. Deviate it up to this point, see there is a slight hinge, so some maxima, deviate it up to here, and immediately at some point the restoring force will start pointing into that direction. So, for small deviation, and the system will fall out of equilibrium. For small deviation from equilibrium position, the system has a restoring force which is driving it back towards equilibrium, and if the deviation is large, it is falling off equilibrium. This is an example of metastable system. And if we have only one minima, something like this, wherever you go, it does not matter. I mean, it will continue like this. I am not giving it a specific shape. Don't even think that this has a form half k x square or half k q square. No, it is not the case. I am just drawing a general potential which has only one minima, and it is extended, the other sides are extended till infinity. So, wherever you deviate, whichever side you deviate it from the equilibrium, this side or that side, the restoring force will always bring it back towards the equilibrium, and this is the example of stable equilibrium. Okay. So, I will stop here, and in the next lecture I will start building things little more mathematically, and we will develop the theories of small oscillation.